Considering circularity in its bigger picture and therefore the design for recycling as a part of that, one needs to understand the system. And I am now doing some applications to show you specifically how you can use the tools that are available to us to actually do rigorous design for recycling of products, also considering modular design, etc. This figure nicely shows that nexus between energy and materials. But a key message, and that will be the key message of this lecture, is that one has to understand all the streams in terms of thermochemistry, ultimately to permit one to quantify the losses from that system and the dissipation of materials in terms of exergy, so that one has one unifying unit with which one is describing the complete system. In other words, the flow of energy or entropy as kilowatt hour per hour. And this will be the key message, that if one truly wants to understand not only the material losses, but the hidden losses as entropy, one needs to use and do simulation as a key tool. And I'd like to show this to you. So many years ago in Holland, when I was full-time professor there, we developed the metal wheel, where we actually tried to show this connectivity between elements in the context of processing, metallurgical processing. So we coined it the metal wheel, where the center ring is what is truly required to make our circularity work. You need a steel industry, you need a copper, nickel, lead, tin industry, not only to bring the metals into the system, but you need the plants also to recover those metals back from the end-of-life products and bring them back into the quality. Remember the quality that is required of the materials, alloys in that product. That's true circularity. Let me just explain this drawing quickly, and it's been a proxy for explaining that complex interaction between elements in a product. So in other words, we have the base metal industry, in this case copper nickel, in this segment of the metal wheel. With it, it brings through the primary side a lot of elements which we recover, but due to its relative nobility, it can also dissolve those elements, which you can subsequently then recover from the copper. These can go various places, say in a copper smelter, into various phases, and that's important, how to manage those phases that capture these elements and then bring them back into the circle. And that's what we really do in the end as metallurgists. In some cases as well, inevitably some materials go lost, which we cannot recover at the moment economically. But an important one is, for instance, slags, which we usually try to produce as a product, which can go into the building industry. But we need to follow and understand all the elements in a product at the same time. And this goes beyond the simple element by element analysis, for instance, of a material flow analysis. In a simulation, you look at them all at the same time, in their chemistry, in all of their compounds. So the green balls in this case are generally recovered. The yellow ones are intermediate. They can be alloying elements, or they can be present in ways where they can be used again. And then there are some cases where elements are simply just lost and cannot be recovered. So what do we have here is the full metal wheel. And I always like to compare this with recycling a cup of coffee. If you look at the copper side, which I explained in a couple of moments ago, and I compare that with a cup of coffee, then that would mean I would use the water in the cup of coffee as the solvent and ultimately recover the sugar, the milk, and the coffee from it. But then you can ask yourself the question, is that possible? And this is a case that I put into the UNEP report on metal recycling for you to ponder about. Because not only do you have to put energy in the system to get it out, but you have to also counter the entropy of solution, the excess energies, to reverse that. That costs money. Looking at the steel side, which has a lot of red balls and also orange balls, implies simply looking at the cup of coffee. If you want to recycle it, and you want to reuse it if that is at all possible, if you don't want to have stale coffee said immediately as well, you can add either more sugar or more water to get exactly the sweetness level that you require. Two different types of metallurgies. One is a dilution metallurgy, the other one is a refining metallurgy. But this is a figure we developed to bring this across already about 20 years ago, to explain the complexities of circularity and recycling in general. So in summary, if you look at a policy brief that we brought out, shown over here, you can read it and download it from the internet, shows, for instance, lead and zinc, its associated elements, where they are used in a household in this case. But lead, among others, is once again the solvent to be used to recycle these elements and bring them back into the cycle. So one needs lead not only as a supplier of technology elements, but also it's a key part of the recycling of that system. This sort of begs the question, and also should put that question mark in your mind. Removing any segment from the metal wheel has the consequence as shown in this figure. Looking specifically, the importance of having a copper and nickel segment in the metal wheel, as you would need all the other segments to keep the wheels of the circular economy turning.